All right, so then objective 3, we want to use time as a parameter in parametric equations. So if we think as t as a parameter of time, then the parametric equations specify how the x and y coordinates of a moving point are going to vary in time. So for example, we can use parametric equations to model the motion of an object, which is sometimes called the curvilinear motion. I think that's how you say that. We can now define where and when an object travels. So according to the where with our x and y, like where an object is going to travel, we can now determine where and when we decide that t is a parameter of time. So when an object is propelled upwards at an inclination of theta to the horizontal with an initial speed of v naught, the resulting motion is then called projectile motion, which may or may not be a term that you've heard before. So the parametric equations of the path of a projectile fired at an inclination theta to the horizontal with an initial speed of v naught or v sub 0 from a height h above the horizontal are going to give us the equations of x of t is equal to v naught times cosine of theta all times t. Then we have y of t is going to be equal to negative 1/2 g times t squared plus v naught times sine of theta times t plus h, where now we see t is going to be time, g is the constant acceleration due to gravity, which is going to be approximately 32 feet per second squared, or 9.8 meters per second squared. So those are our values for gravity in that case. And if you think about it, x is along the horizontal, y would be our vertical. If we are firing a projectile up into the air, gravity is going to be affecting the vertical distance of that object, so gravity applies to y. All right. So an applied problem here, we want to suppose that Jim hit a golf ball with an initial speed of 150 feet per second at an angle of 30 degrees to the horizontal. So we can see this in our figure here. For part A, we want to find parametric equations that describe the position of the ball as a function of time. B, we want to know how long was the golf ball in the air. C, when the ball was at its maximum height, or we want to know when. And then we want to find the maximum height of the ball. And then D, we want to find the distance that the ball traveled. So quite a few parts here. Let's start breaking it down. So part A is just asking us to define the parametric equations of this situation. And we know our parametric equations are going to end up looking like this, so we really just have to go ahead and define all the different parts. So for part A, we can go ahead and define our different variables. So we have in this case that v naught, or the initial speed, is 150 feet per second. So we have our value of v naught. Our angle, theta, is going to be 30 degrees. Then we have h, our height. Our current height, or our starting height, is going to be 0 feet. And this is because our golf ball is on the ground. Since golf ball is on the ground. So our height before Jim has hit this ball, so we're describing the initial position here, our height is going to end up being 0. Then our last value here, is gravity. We see that all of our values are going to be in feet, so that means that we have to use our 32 feet per second squared. So gravity is equal to 32 feet per second squared. So we've defined all of our values. So you can say now we can plug these values. into equations 2. To get our parametric equations. So x of t we see is v naught times cosine of theta times t. So we get v naught cosine of theta times t. This is going to end up giving us 150 times cosine of 30 degrees times t, which is going to simplify to 150 times the square root 3 over 2 times t, where we can combine 150 and the square root of 3 over 2. We can divide 150 by 2 and then multiply by square root of 3. So this just turns into 75 times the square root of 3t. So x of t is equal to 75 times the square root of 3t. Then for y of t, our equation was negative 1/2 g times t squared plus v naught sine of theta times t plus h. So simplifying this equation, we can get that this is going to be equal to negative 1/2 times 32 times t squared plus 150 times sine of 30 degrees times t plus 0. Simplifying this problem, we end up getting negative 16 t squared plus 150 times sine of 30 degrees. Sine of 30 degrees can be 1/2. So 150 times 1/2 is 75 t. So we have that our parametric equation y of t is equal to negative 16 t squared plus 75 t. So that is one of our answers. So we can actually highlight that in yellow, not in blue here. So now on to part B. Part B wants to know how long was the golf ball in the air? So to find how long the golf ball was in the air for, we want to solve for y of t being equal to 0. So for solving for y of t being equal to 0, we know that y of t is equal to negative 16 t squared plus 75 t. And now we're setting this equation equal to 0. The one thing that we can factor out of negative 16t squared and plus 75t is t itself. So we can say t times negative 16t plus 75 is equal to 0. This automatically means that one of our values of t has to be equal to 0. Then we can also get, so we'll do a little arrow there and here. So we get that t is equal to 0 or negative 16t plus 75 is equal to 0, which means that we can end up getting negative 16t is equal to negative 75. So then t is equal to 75 divided by 16, since both of those negatives get canceled out. And let's actually bring this down a little bit here. So t is equal to 75 divided by 16, which we have to use a calculator to find the value. And this is going to be equal to 4.6875 seconds. So that gives us our value of t for when y of t was equal to 0. So when y of t is equal to 0, this essentially means what were the times when the ball was touching the ground. So the ball was on the ground at the initial point and then at the end. And then solving for that value of t gives us how long it was not touching the ground. So we can say that, so the ball hit the ground after 4.6875 seconds. Depending on if this question was asked in my math lab, it may say round to a specific amount of decimal points. So in that case, you would want to round this value, but sometimes it's not exactly necessary. All right, then for part C, we want to know when was the ball at its maximum height, and then also what was the maximum height. So to do this, we can say that the height, y, of the ball is in a quadratic form, meaning that we have a t squared term. So it's in a quadratic form, or just that it's a quadratic function. So the max height is found from the vertex. So a little bit thinking here about similar to equation 1 where we had that parabola where it has a specific vertex at a specific point. So since our equation y is a quadratic function, our maximum height is going to be found at the vertex of y of 2. Which we know y of 2 is equal to negative 16t squared plus 75t. 75. So we can get then that negative 75 divided by negative 32 is going to be equal to 2.34375 seconds. Another way you could have found this value was by dividing 4.6875 in half. Assuming that the max height was at exactly halfway was in the air, and you could also get this value. So we get that the max height for the ball, the ball was at max height at 2.34375 seconds. So plug this value in. For t and y of t to get the height. Just defining that answer first, because it asks us two things. We want to know when the ball hit its maximum height and then what that maximum height was. So we found when it hit its maximum height. So then the actual value of the height is going to be, if we plug in 2.34375, into the equation of y of t, this would end up giving us 16 times 2.34375 squared plus 75 times 2.34375, which of course you want to plug that into a calculator, and when we do, we get that's going to be equal to 87.89 feet. So the max height in this case, was found by using when we had that max height occur, we used that time to plug into our equation to actually find the actual max height, which we got was about 87.89 feet. Then our last question, part D, we want to find the distance that the ball traveled. Don't know if we'll have enough room, but let's try and fit this in. So if the ball was in the air for 4.6875 seconds, then the horizontal distance is x equal to, and now we plug in that value of t. So this would be x is equal to 75 times the square root of t times 4.6875, which we want to use a calculator for this. And when we do, we end up getting the ball traveled 608.92 feet. So there we go, fit that in. So once you know how long the ball was in the air for, so the vertical calculation of time, then you can go ahead, plug that value of time into your horizontal distance equation, which is x in this case, to go ahead and find how far it traveled horizontally. So, all right, quite the problem there, quite a bit long, but we can see how useful having these parametric equations can be, especially in things like applied problems. Problems like these will come up quite often, most often in calculus. So getting a hang of these now can be pretty helpful in the future if you want to go ahead and take calculus as well. All right. Now our last objective, we have objective 4, find parametric equations for plane curves defined by rectangular equations. So if a plane curve is defined by y is equal to f of x, we can let x equal to t and get that x of t is equal to t, such that y of t is now equal to f of t, or t is in the domain of f, as our parametric equations. So we're really just stating here that if we have our rectangular equation y is equal to f of x, we can replace x with x of t, where x of t is equal to t, to easily get a new equation of y is equal to f of t, since we replaced x with t. So we can go ahead and do an example of this. So example 4, we want to find two different pairs of parametric equations for the function y is equal to x squared minus 4. The easiest example in this case is a direct correlation. We can just let x equal t. So for the first pair, we can just let x be equal to t. And if we let x equal to t, then we get that x of t is equal to t, such that now y of t is equal to t squared minus 4. And t is now defined between negative infinity and infinity. We can define it from negative infinity to infinity solely because there is no place that t can't exist, so we say that t exists everywhere. So that was our first pair. The direct correlation is always the easiest pair you can make. Now, the next pair we can find another pair of equations. And for our question, we're going to use x of t is going to be equal to t cubed. So if we use x of t is equal to t cubed, then y of t is now going to be equal to t to the power of 3. So we replace x directly. So one single x is equal to t to the power of 3, now squared, since we had x squared. Minus 4. This simplifies to y of t is equal to t to the power of 6 minus 4, where we see that t is still defined between infinity, negative infinity, and infinity. So here's one answer, and here's another. So for the domain parts, all you need to do is you just have to pick equivalent values of t that would still allow your domain to be the same. And that's really the only thing that you have to make sure of when you replace these values of t. You just have to make sure that it can be solved and that you're staying within the same domain as before. So, all right, that wraps up our section on 10.7. So I'll see you all for our very last section, 11.5.